Yes. So we can say that surface chemistry is basically chemistry
that happens at the surface.
on surface of something, right? It can be anything.
Okay.
So usually we hear that in rainy season most of the iron substances get rusted.
Mm-hmm.
So do you think we can relate that rusting of iron to surface chemistry?
Let's see.
Okay, I'll give you an example.
Okay.
If we consider an iron rod, let us think that this is an iron rod. And usually we can see that one layer deposits on the surface of iron. If we just remove that, inner surface will be still iron.
Correct.
It won't affect that. So only the particles will be deposited on the surface. That's what we call as rust.
Okay. And you're saying that that is a surface phenomena, right?
Yes.
That's correct. Okay. So this is surface chemistry.
So this is surface chemistry because the reaction has taken place only on the surface and not has taken place inside the substance.
Alright, okay.
So now this rust is nothing but, in chemical terms we call this as hydrated ferric oxide.
That's the
That's
chemical
the chemical
name
name for rust.
Okay. Don't you want to write a chemical formula there? I'm pretty sure our viewers would want to know the chemical formula.
Okay, it is Fe2O3 3H2O.
This is the hydrated part. Right?
This is hydrated part and this is
That's
ferric
the ferric
oxide.
oxide. Okay.
So, in surface chemistry, we have names for rust as well as iron rod.
Okay.
So, some particles which is sitting on the surface of anything is called adsorbate.
Adsorbate. Okay.
And the substance on which the particle sits on, it is called adsorbent.
Okay.
So in this, rust becomes adsorbate because it is sitting on the substance, and iron rod becomes adsorbent because the rust sits on the iron rod.
Okay.
So we can give one more example of duster and chalk.
Okay.
We usually see in our schools or colleges that every time we write something and we keep dusting the board.
Correct.
And while dusting, where do you think the particles will be?
The chalk particles, right?
Yes. If I consider this as a duster, and after dusting, the particles, do you see that it gets accumulated on the dust?
Yes,
on
very
the
much.
duster?
Not only on the duster, also on me and my pants.
So this is a duster.
Oh, that's a surface phenomena as well.
Yes.
Okay.
And these are the particles.
Chalk particles.
Yes. So now can you tell me which is adsorbate and which is adsorbent?
Comparing with this, just like how rust was the adsorbate here, I think the chalk particles are the adsorbate here.
Correct. So these are adsorbate.
And the surface of the duster becomes the adsorbent.
Very good. This is adsorbent.
Yay. Okay.
So we have a technical term for this, that is adsorption.
So this phenomenon is what we call as adsorption, right?
Yes. So now what adsorption is? We can see some particles are getting accumulated on the surface of a solid substance or any substance for that matter. That is called adsorption. So adsorption is?
Phenomena where some particles which we call as adsorbate sit on some surface which we call as adsorbent.
Correct. So the particles sits on something.
Okay, that's nice. It's easy to understand.
So what are particles here?
Adsorbate.
Yes. Particles are adsorbate.
I'm getting this.
And that's something I can call now that has a substance.
Okay.
And that is now
Adsorbent.
adsorbent. So you might have heard sometimes we also make use of the term absorption.
Oh yeah.
So what do you think is the difference between absorption and adsorption?
There's a D here, there's a B there.
Okay, that's not the only difference. So if I consider a ball, and inside this ball let me take some water.
H2O.
Yes. Very good, you're learning something. So now if I take a sponge. Okay, let us consider this to be a sponge. Or we can also take tissue paper.
Okay.
What happens if I dip this sponge in water?
The sponge gets all soaked up and wet and it absorbs water. Oh, that's absorption, right? It
Yes.
absorbs water.
So
Correct.
you can see that the water particles now move into the sponge.
Correct.
That means if this is a sponge now, the water particles are present inside this. Do you see water particles only at the surface
No.
as that of this?
No.
No. It is moving into the bulk.
Correct.
Therefore now this is called,
This is the bulk phenomena.
this is the bulk phenomenon.
Ooh, so surface chemistry. Oh yeah, I get it now. Adsorption is the surface phenomena and absorption is the bulk phenomena.
Yes.
That's the major difference.
That's the
right?
major difference between absorption and adsorption. So I can say now the particles,
They move into the substance, right?
yes, move into the substance.
I think that's the key point. It sits on something here, but this moves into it.
Yes.
You know that the accumulation of molecular species on the surface of a solid or liquid, resulting in a higher concentration of the molecules on the surface, is known as adsorption. Adsorption of gases on solids can be of two types: physical adsorption and chemical adsorption. Let us discuss physical adsorption first. When gas molecules or atoms are held to the surface of a solid by weak van der Waals forces, then it is called physical adsorption. Physical adsorption is also known as physisorption or van der Waals adsorption. Let's look at an example. In the adsorption of dihydrogen on the surface of finely divided platinum, hydrogen molecules are first attracted towards the surface of platinum by weak van der Waals forces, and then adsorbed due to the presence of unbalanced attractive forces or free valencies on the metal surface. This is physical adsorption. Here, platinum is the adsorbent and dihydrogen molecules the adsorbate. Note that there is no chemical bonding between the adsorbent and the adsorbate. Thus, we can also say that physical adsorption occurs when a gas accumulates on the surface of a solid by van der Waals forces without the formation of a chemical bond between the adsorbate and the adsorbent. Now let us discuss chemical adsorption. Chemical adsorption or chemisorption is defined as the phenomenon that occurs when gas molecules or atoms are held to the surface of a solid by chemical bonds. In the example of dihydrogen and platinum, on increasing the temperature, the adsorbed dihydrogen molecules on the surface of platinum dissociate into hydrogen atoms. These hydrogen atoms are held strongly by platinum through chemical bonds. The chemical bond can be ionic or covalent in nature. In some cases, both physical and chemical adsorption may take place at the same time, and it may not be possible to identify the types of adsorption. The basic characteristics of adsorption depend on the specificity of the adsorbent, nature of the adsorbate, reversibility of the process, enthalpy of adsorption, activation energy, layers of adsorption, and surface area of the adsorbent. Let us discuss how each of these characteristics affects physical and chemical adsorption. In physical adsorption, the surface of the solid or the adsorbent has no specific preference for any type of gas molecules or the adsorbate, because the van der Waals forces that act on the adsorbent and the adsorbate are universal. However, chemical adsorption is highly specific and will occur only when an ionic or covalent bonding is possible between the adsorbent and the adsorbate. Therefore, we can infer that while physical adsorption is not specific in nature, chemical adsorption is highly specific. The amount of gas absorbed by the adsorbent also depends on the nature of the gas or the adsorbate. Different gases are absorbed to different extents by the same adsorbent at the same temperature. For example, at 288 Kelvin, 1 gram of charcoal absorbs 380 cc of sulfur dioxide, 16.2 cc of methane, and only 4.5 cc of hydrogen. The volumes of sulfur dioxide, methane, and hydrogen are reported at STP conditions. It may be seen from the critical temperature values that higher the critical temperature of a gas, the greater is the extent of adsorption. This is because gases that can be easily liquefied have high critical temperatures and are more easily adsorbed. This can be attributed to the fact that the van der Waals forces are strong in the range closer to the critical temperature of that gas. The critical temperature of a gas is defined as the temperature above which the gas cannot be liquefied, however high the pressure applied. It can be seen that the volume of the adsorbed gas increases as the critical temperature increases. The critical temperature of sulfur dioxide is 430 Kelvin, and hence, it is adsorbed more on charcoal than methane and hydrogen, which have a critical temperature of 190 and 33 Kelvin respectively. In chemical adsorption, no correlation is seen between the amount of gas absorbed and the critical temperature of the gas, but adsorption depends on the chemical nature of the gas. The greater the reactivity of the adsorbate, the greater is the amount of adsorption. Therefore, we can infer that both physical and chemical adsorption depend on the nature of the adsorbate. Let us now discuss the reversible nature of the process. Like any other equilibrium, adsorption is a process involving true equilibrium, with adsorption on one side and desorption on the other. The two opposite processes include the adsorption of gas molecules on the surface of a solid and desorption of gas molecules from the surface of a solid into the gaseous phase. You know that adsorption is an exothermic process. The equilibrium can be represented as gas, the adsorbate, plus solid. The adsorbent is in equilibrium with the gas adsorbed on the solid plus heat. On applying Le Chatelier's principle, it can be seen that when we increase the pressure or decrease the temperature, the equilibrium shifts forward. That is, adsorption increases. Similarly, when we decrease the pressure or increase the temperature, the equilibrium shifts backwards. That is, adsorption decreases. In other words, desorption takes place. For example, 1 gram of charcoal absorbs about 10 cc of nitrogen at 273 Kelvin, 20 cc at 244 Kelvin, and 45 cc at 195 Kelvin. It is observed that adsorption of nitrogen on charcoal decreases with an increase in the temperature. Thus, we can say that physical adsorption is a reversible process due to the presence of weak van der Waals forces of attraction. However, during chemical adsorption, chemical bonds are formed between the adsorbate and the adsorbent molecules. For example, when oxygen is chemically adsorbed on carbon. To reverse this process, there is a need to free the adsorbed gas. However, the reverse process releases carbon monoxide or carbon dioxide instead of oxygen. Hence, chemical adsorption is irreversible in nature. Therefore, we can conclude that while physical adsorption is a reversible process, chemical adsorption is irreversible. Next, let us discuss the enthalpy change associated with physical and chemical adsorption. In physical adsorption, since the van der Waals forces of attraction are weak, the heat evolved or the enthalpy of adsorption is very little, around 20 to 40 kilojoules per mole. Chemical adsorption is also an exothermic process. However, in chemical adsorption, surface compounds form, and the forces involved are similar to chemical bonds. Thus, a relatively high amount of heat is evolved, about 80 to 240 kilojoules per mole. Therefore, we see that the enthalpy of physical adsorption is low, whereas the enthalpy of chemical adsorption is very high. Let us now discuss the activation energy required for adsorption. Activation energy is the minimum energy required to convert reactants into the respective products. Physical adsorption involves only weak van der Waals forces and does not involve the formation of surface compounds or any chemical bonds. Therefore, it does not require activation energy. However, as chemical adsorption involves the formation of surface compounds, activation energy is required for the formation of chemical bonds between the adsorbent and the adsorbate. A gas may be physically adsorbed at low temperature, but chemisorbed at high temperature. During the adsorption of hydrogen on nickel at low temperatures, hydrogen is physically adsorbed on nickel. However, at high temperatures, hydrogen gets chemisorbed on the surface of nickel. In other words, an increase in the temperature supplies the necessary activation energy for the formation of surface compounds, and the process is called activated adsorption. We can therefore conclude that physical adsorption requires no appreciable activation energy, while chemical adsorption requires high activation energy. Let us look at the type of molecular layers that are formed during physical and chemical adsorption. Layers of gas molecules are adsorbed one over another by van der Waals forces in physical adsorption. That is why multimolecular layers are formed under high pressure in physical adsorption. In chemical adsorption, a chemical bond is formed with the molecules that come in direct contact with the surface of the adsorbent. Hence, only a unimolecular layer is formed in chemical adsorption. Therefore, multimolecular layers are formed in physical adsorption, but only a unimolecular layer is formed during chemical adsorption. Let us now look at the impact of the surface area of the adsorbent on physical and chemical adsorption. The greater the surface area, the greater is the adsorption. Therefore, substances with porous structures are good adsorbents. Charcoal is a good adsorbent as it has a porous structure. For both physical and chemical adsorption, the extent of adsorption increases with an increase in the surface area of the adsorbent.
This topic is Langmuir adsorption isotherm. This isotherm, this theory was firstly proposed by Langmuir in 1916 to describe the adsorption of the gases on the surface of the solids. The basic assumptions that are made in this theory are that the surface of the solid is made up of elementary sides, and these sides can absorb the gas molecules. It means these are the sides on which the gas molecules are being absorbed. Suppose I have made this a general diagram for your convenience. In this diagram you can see this is any solid surface, and on this surface there are certain sides. These are the sides that are present on the solid surface, and on these sides the gas molecules can be absorbed. Suppose this is the gas that is present. Now the absorption of the gas molecules can take place on these sides. These sides will absorb the gas molecules, and on each side only one molecule will be absorbed. It means any side cannot absorb the two molecules. Only one molecule will be accommodate, one molecule or atom on anything will be absorbed on the one side. Another assumption is that the surface of the solid is homogeneous. What is meant by homogeneous? It means all the sides are equivalent. Suppose this is the solid surface. This is a two-dimensional structure, and this is a solid surface that is homogeneous. It means all these sides, these are the sides. These are the sides on which the gas molecules are being absorbed. All the sides are same. It means they will have the same affinity for the gas molecules. It cannot happen that the one side can absorb easily than the other side. All will have the same affinity. And the absorbed gas molecules behaves ideally in the vapor phase. The third assumption is that the absorbed gas behaves ideally in the vapor phase. And the fourth assumption is that only monolayer is formed on the surface of the solid. It means these gas molecules that are being absorbed will form only a single layer on the surface of the solid. Why? Because there are the sides on which these molecules are being absorbed. So there is no chances that there can be formed a second layer. Only a monolayer will be formed on the surface of the solid. This is the assumption that is made in the Langmuir adsorption isotherm. Further, it was said that there is no lateral interaction between the gas molecules that are being absorbed. It means these molecules. Here we have shown by these blue dots, these blue marks. These are the gas molecules that are being absorbed. This will be single molecule. These are the gas molecules that are being absorbed. So there is no chance that this and this gas molecule can interact, or this can interact. There cannot be interaction. There is no chance of the formation of another product on these sides. These does not react with each other, and these absorbed molecules are localized. It means there is no chance that these molecules can move from their position. These are being absorbed and this will not move from their position. These remains as it is. It means these are immobilized. So from this structure we can understand this is a solid surface that is quite homogeneous. All the sides have the same affinity. The gas behaves ideally. A single layer is formed on the surface of the solid, and these are the sides that are being occupied. So we will call them occupied sides. And these are the sides that I have denoted by the red marks. These are the unoccupied sides. Hello students. Our today's topic is BET theory for the multi-layer adsorptions on the solid surface. This theory was given by Brunner, Emmett and Taylor in 1938. So this theory is also known as the BET theory. The basic assumptions that are made in this theory are that the solid surface has the uniform and localized side, as this is the same as that was assumed in the Langmuir adsorption isotherm. The solid surface is here also assumed to be uniform, and there are the localized sides on which the adsorption of the gas molecules takes place. The adsorption on one side is independent. It is not affected by the adsorption on the another side. So each side is independent. But in this theorem, it was assumed that the multi-layers are formed. In the Langmuir adsorption isotherm, what was assumed? The assumption was that the monolayer is formed on the surface of solid. But in this theorem, it was assumed that the multi-layer is formed, and the surface area for nth layer depends upon the fraction covered of n minus 1th layer. We can understand it with the help of the example. Suppose this is a solid surface. On this surface, a monolayer of the gas is formed firstly, and then on this layer the another layers can be formed. This is the second layer that is formed above this first layer, and the third layer is formed above the second layer, and the fourth layer is formed above the third layer, and in this manner different layers can be formed upon the lower layer. So the molecules of the second layer sit on the molecules of the first layer. The molecules of the third layer sit on the molecules of the second layer. So here we can see that for the first layer, their adsorption depends upon the surface area of the solid, that is vacant. But for the second layer, it does not depend on the surface of the solid, because these are being adsorbed on the surface of the molecules of the gas. It means these are sitting on these molecules. So this will depend upon the surface area of this side, this first layer, the surface area vacant on the first layer. Similarly, the adsorption of the third layer will depend upon the surface area of the second layer, that is vacant, that is present, on which these molecules can sit. So we can say that the surface area for the nth layer is directly proportional to the fraction that is vacant on the n minus 1 layer. And the heat of the adsorption for the first layer, here it is assumed that the heat of the adsorption for the first layer is constant, while the heat of adsorption for the succeeding layer is dependent. It is equal to the energy of the liquefaction of the gases. It means the heat of adsorption in the succeeding layer, all layers are same. For the heat of adsorption for the all successive layers are same, and it is equal to the energy of liquefaction.